We've talked about use of global and local coordinate systems with projectile motion. Let's now talk about using global and local coordinate systems when using Newton's second law to solve problems. As it turns out, everything is really the same. So here's an example. We have two boxes tied together by a rope, and maybe somebody has their hands and they're pulling the boxes along on their own. All right. In any case, they're creating a force F to the right on M2. So to solve this problem, you can create free body diagrams for both masses. So for M1 and for M2. And we have gravity going down for both of them. We have a normal force going up for both of them. For M1, there's a tension force pulling it to the right. And for M2, there's a tension force pulling it from the left. And it'll be the same magnitude as the tension force from block 1 because it's just one rope and tension is the same in a rope. And then we have to the right on M2 this force F. So from here, you could use Newton's second law to create equations using F equals ma. To do that, though, you have to choose a coordinate system. And normally, you just choose a coordinate system, maybe something like this, right? So up is positive and to the right is positive. And you use a global coordinate system because that's the thing that will make the most sense in our problem. So let's go ahead and do that so we can see what the equations are. In that case, for M1, in the x direction and the y direction, and then we have M2, the equations in the x and the y. So in the x direction for M1, we have t is going to the right, so it's positive, equals M1a. Technically, it's an A1, but since the whole system is moving together, the acceleration is going to be the same for all the objects in the system. And then in the y direction, we have, but it's moving only in the horizontal direction. There's no acceleration in the y direction, so you get 0. All right, then you can do something similar for M2. And now we have a force F to the right, tension to the left is M2a. And we have N2 minus M2g is equal to 0. All right, so that's what we did. If we wanted, though, we could have solved this problem a little bit of a different way. We could have created a coordinate system for each of our objects. So we could have created one coordinate system for one object, and we could have created another coordinate system for the other object. In general, you can create a local coordinate system for each free body diagram that you draw, so for each object in your system. In this case, if I make coordinate systems like this, it doesn't really make a whole lot of sense because the directions are the same and we aren't really keeping track of the motion of the objects as we were in kinematics. Sometimes you do that because sometimes you will use Newton's second law to get acceleration, then use that acceleration as input to kinematics equations to keep track of the motion of your object. But just for fun, if I wanted to, let's suppose I created a coordinate system for M2, a local coordinate system like this. So my direction in the x direction is different. How would my equations change? Well, for M1, the equations are going to be the same. I'm not keeping track of the motion of the object, so the exact placement of the origin doesn't matter. The only thing that matters is the direction of the axes, and they're still in the same direction as the global coordinate system that I had drawn previously, right? So these equations stay the same in the red coordinate system. In the blue coordinate system, the y direction stays the same because the only thing that mattered there was direction. But now, in the x direction, something is different. I made to the left positive. So now I get t minus f is equal to m2. And now I'm going to call it a2. All right. Now let's think about what's going on with a2 in comparison with a1 if I was to write out my equation like this. The acceleration is to the right. I'm pulling things to the right. All right. Well, if I'm pulling things to the right is the positive direction for m1. And so I can indeed just write m1a, where I have my acceleration a to the right. But my acceleration a to the right is negative in the blue coordinate system because to the right in the blue coordinate system is negative. So I could write this equation as m2 minus a, or in other words, minus m2a. But wait a minute, I can divide by the negative sign on both sides of this equation, right? T minus f equals minus m2a. If I do that, then this flips around and I get minus t minus f. If I distribute the minus sign, I get minus t plus f, or in other words, I get f minus t. And on the right-hand side, I divide it by negative 1, so I get n2a. And would you look at that, I get the same equation as I had before. This is a pretty general property. For the coordinate systems and Newton's second law, you will get the same system of equations out no matter which coordinate system that you use. And that'll be true whether you use different global coordinate systems or you use different local coordinate systems and then stitch your coordinate systems together. Usually, you'll stitch your coordinate systems together when using Newton's second law by finding what the acceleration vector should be. So I knew my acceleration in the red coordinate system was to the right and therefore positive, but since my acceleration is to the right in my blue coordinate system, it was a negative acceleration, but they had the same magnitude because they're both moving as one object.